1-7 infinite series. Okay, does it make sense to talk about adding infinitely many numbers? You might think it's impossible because it would take infinite amount of time, but there's a situation in which implicitly use infinite sums. For instance, the decimal notation of 0.4 repeating as it's going on forever. Okay, can be represented in this pattern: 4/10 plus 4/100 plus 4/1000, etc. That's an infinite series because you keep adding on that next hundredth or thousandth. You can also write that, though, as a 4/9 as a fraction. So it does have a value is the point. Okay? So this just going on the idea that, well, you think that, yeah, some numbers, if I'm doing 2 plus 2 plus 2 forever, that's not going to have a value we can measure because that's going to essentially just go to infinity. It's going to keep going forever. If I keep going 2 plus 2, which is 4, then 6, then 8, now that infinite sum would be one example of like that divergent convergent. That'd be divergent in the sense that it wouldn't really approach anything. Remember, we talked about last class in terms of sequences can approach something. Your sums can also approach something to actually a value. In this case, the number 0.4 repeating is an infinite sum of these values, which we can convert to the fraction 4/9. So in terms of another, like a Zeno's paradox, and that was mentioned in the last notes, we didn't really go over it specifically, but another situation that gives an infinite sum occurs in one of Zeno's paradox as passed by Aristotle. A man standing in a room cannot walk to the wall. In order to do so, he would first have to go half the distance, then half the remaining, then again half. This process can always be continued and can never be ended. So if you're always halving something, technically you won't ever get to an end, but we will be approaching something, right, with the idea of a limit. We talked about this idea when we were in Math 20. We talked about with a pizza. If you cut a pizza in half, you keep doing it, at some point you can't cut that thing in half. Okay, and that's where you're going to kind of essentially it's going to approach something. Okay, so but of course we know that a man can actually reach the wall. Okay, we know he'll actually get there. So this suggests that perhaps the total distance can be expressed as this sum: 1/2 plus 1/4 plus 1/8 plus 1/16, etc. has to equal 1. Well, how does that help us? Well, if I have 1/2, gets 0.5. 1/2 plus 1/4 is 0.75. 1/2 plus 1/4 plus 1/8 is 0.875, and etc. And you can see it's getting closer and closer to the number 1 here. Okay. So notice as we add more terms, the partial sums become closer and closer to 1. In fact, by making n large enough, that is by adding sufficiently many terms of the series, we can make the partial sum as close as we like to the number 1. So therefore, it seems reasonable to say that the sum of the infinite series is 1, because we know he's going to eventually, guys, he has to get there. It's kind of like, I know we can play devil's advocate and say, well, no, he's not quite going to be there. Well, not quite going to be there. Then I can say, well, his nose is long enough, he's going to make it, from where his toes are. Who knows? Okay? But the point is, he's going to get there. And so when we say limit as n goes to infinity, so we're saying, hey, the max in value, he's going to reach the wall. Reaching the wall is the value of 1. Okay? That's the end value. Same thing. What's the end result of keep eating half the pizza? At the end of the day, you're going to eat the whole thing. Okay? At the end of the day, it'd be your infinite at the end. Okay? So keeping that in mind. So we use a similar idea to determine whether or not a general series of terms has a sum. So do they approach something? So what's the situation where it does approach and when it doesn't? So when you're doing infinite series, you have to first signify, is it approaching something? Like, is it approaching a wall? Is it approaching eating the whole pizza? Or is it too big and going too high? In other words, it's diverging away from a possible value. So your very first thing with the infinite series is that you have to recognize, is it a situation that's approaching something, or is it a situation that's like taking off in a big or a really big number or a really small number direction, which would be divergent. Okay, the convergent divergent idea. All right. So infinite sequence, partial sums of the series has a limit. We say the sum of the series, well, then we write it like so. We use sigma notation if it does have a limit. If it doesn't, okay, it's called convergent if it does. If it doesn't, we call it divergent. I already went over that. Convergent means it is approaching something. Divergent means it's not approaching anything. Okay, it's going too big that it doesn't matter, or it's going too small, like it might be like a big negative number, it doesn't matter. Okay, any questions with that? So simply, we're going to get to this. It's basically going to be a formula. Okay, and that's all it is, just like when we did sequences and series in Math 20, really formula-based, so it shouldn't be that big of a deal. All right, let's get to the examples. Everybody good with that? I zipped through that a little bit because, again, it is a concept you have heard before. But is there any questions on convergent, divergent? For sure? Okay. So example 1, determine whether the following series are convergent or divergent. Okay, so A, 1 plus 1 plus 1 plus 1. Yeah, A is divergent, right? Because it's going up by 1 forever, but it's never approaching anything. So it's essentially going to be infinity, okay, which isn't going to give us a value. So this one right here is divergent for A. How about B? We kind of talked about this one in the last lesson in terms of the one that was bouncing. It's bouncing back and forth, but it's not approaching anything. So it's going plus 1, minus 1, plus 1, minus 1. So it just keeps hopping the bridge. So it's not approaching anything at all. So these are both divergent examples of patterns because they are not converging to a specific value. Does that make sense? I know, like, is anybody in here, let's just look. This is my first thought I looked at this. But on this one, is anybody saying it's converging to 0? I mean, my first thought was it's converging to 0. I'm adding 1, minusing 1, adding 1, minus 1. But I'm off 0, I'm on 0. I'm off 0, I'm on 0. So I keep going away from it. It's the part that's making it not convergent. Does that make sense? It's not approaching 0. It's hitting 0. Okay? All right, good. So that's divergent for both of those. Find the sum of the geometric series a plus a to the r plus a to the r squared plus a to the r minus 1. A cannot be 0 when it exists. So what we're going to do essentially is we're going to use, and I don't think, did I skim over that? Yeah, so we're going to do kind of sigma notation. We're going to do from infinity from 1 of the term equals the limit. And I don't think, let me look here. Yeah, this is the formula we're going to use. We've used this in Math 20. The sum of a series that you can do when it is convergent is a over 1 minus r. Okay, in this term. So a is the constant. R is like the variable that's growing, like the term, like the thing that's changing in terms of like an exponent. Okay, so we'll look at that last one here in a second, but we're going to be using this formula right here. So I put that up there because we're doing a over 1 minus r. So essentially what we're building, essentially this is having us build that formula, so I'm kind of going backwards here. But if we were setting it up based off this, like the definition of a sum, it would be a to the 1 minus r to the n all over 1 minus r. That's what the S sub n would be for this specific. Okay. And this is like, I'm not going to really unfold this for you because I feel like that just confuses people. Maybe I confuse you by putting this up here, but this is what you need to know, is it comes from the idea of a limit. So let me just go to this next one here. So this is what you want to write down. In sigma notation, this is what we were kind of just that previous slide, the relationship between these two. Remember, what this means, absolute value of r is less than 1. That means you can have a negative or positive fraction under 1. So negative 2/3, positive 2/3 are acceptable for convergent values. R is essentially your rate. R is what it's going up by or timesing by. Okay? So keep that in mind. So the rate can't be bigger than 1. If it's bigger than 1, it's divergent. If it's bigger than negative 1, it's divergent, like negative 4. Like a big negative. All right, think we're going to go through some cases here. Maybe I just did the examples. Yeah, I think I did. That's okay. All right, so this one here, find the sum of the series. So the first term, A. So remember, A is, sorry, maybe I should have said this at the beginning. That's first term. R is the rate, or what is changing. So our first term for this example is 16. And then can anybody see what's the rate? What do I have to multiply 16 by to get 12? Negative what? Close. You have the reciprocal, like it's 3/4. It's going down by 1/4, but you multiply by 3/4, right? So it's 3/4, and it's negative. Why I know it's negative? Because the sign keeps flipping. Whenever you have a flipping sign for a pattern, that means you have a negative r, because your r keeps flipping it back and forth. So my r is negative 3/4 here. Does that make sense? And so now we simply can use the formula A over 1 minus r, which is a negative 3/4, that's plus 3/4. So it essentially is going to be 16 over 7/4. When you do that out, it's going to give you 64 over 7. So 64 over 7 is the sum of that series. Yep, so you can simply do that by simply dividing t2 by t1 every time. So like negative 12 over 16, that gets you negative 3/4. 9 over negative 12, that gets you negative 3/4. You always can do the previous term, sorry. That's how you can always figure it out. Divide this by this by this, etc. Keep doing that. Will get you the r. So just in general terms, guys, t to the n over t to the n minus 1 will get you your r. So t to the n, like the term. So term 2 divided by term 1. 2 minus 1 is 1, 2. That's what that means in notation. Okay, and we're going to do one of those repeating decimal examples now. Okay. All right, so express repeating decimal 2.135 as a fraction. So we're going to do this not using our calculator. Okay, we're going to do this in terms of writing out the series. So this series we could write out as 2.1 plus 35 over 1,000, right? Because 35 is in the thousands place. Plus 35 over 10,000. Or no, it's going to be 100,000. Plus 35 over 2 more zeros. 5. 7. 10 million, and then etc. So do I want my a to be 2.1 here? Do I want my a to be 2.1 here? No. No guesses? We don't, because 2.1 is not part of the repeating pattern. So we really want to kind of look at this piece. But when we do our thing, we're going to add 2.1 at the end in terms of what the value is. Okay, but we're not, like, we're looking at the pattern of 35 repeating. Does that make sense? Okay, so we need to figure this out. So we got to figure out, so in this case, we're going to make a be 35 over 1,000. Okay, what's the R? How many zeros are added each time? How do you signify that with a fraction? 1 over 100. R is 1 over 100. If you're not sure how to get that, guys, you can take this divided by this and you'll get it. Okay? But I would hope that you understand if this is getting smaller, I need to times it by a pretty small number. 1 over 100 is a small number. Okay? This adds 2 zeros. That's why Chris said 100. Okay? All right, so that's my A, that's my R, and so now we're essentially ready to set it up. Okay, so we can say, R, this is how you're going to write it. You're going to write 2.1 plus A, 35 over 1,000, minus 1 minus 1 over 100. Questions? Yeah, we still have, that's still part of the value. And so it's like kind of like we're cutting off a chunk of the value and we're going to add it back on at the end. We good? Okay, and so then now we go ahead and do this, and we're going to get 2.1 plus, that's essentially 0.99, but you can do however you'd like. And when you divide that, I get 35 over 990. Then just to stay away from my calculator and kind of keep everything the same, I write this as 21 over 10. And when I added those as fractions, it gives me, you get a common denominator, I'm going to skip that step, but you get 1057 over 495 is equivalent to this value, if you can check that in your calculator. So 1057 divided by 495 is equivalent to 2.135 repeating. And that's how we can use infinite series to help us do that. Okay? Any questions? That's all for today. All right. We have used that formula before. That's